again, first of all, for inviting me to give this lecture today. So I understand that the audience is mostly master student and PhD student. Is that correct?
Yeah, master student, PhD student. Also, some new faculties are also there.
Okay.
So they are very new in this AI or machine learning field. So you can start in your way.
Okay. Thanks again. So the topic I have suggested is laser welding systems into the era of digital manufacturing. Why is that? Because obviously this workshop is about artificial intelligence in material processing. So my main area is laser welding. So this fits quite well within material engineering. But we also do research and applications of digital technologies like machine learning and artificial intelligence. So that's why I thought one topic for today is basically combining laser material processing, so laser welding, with digital manufacturing. So now, without wasting too much time in introduction, so let me go directly to the main points. So we have two main topics for today, or two main, let's say, areas. So the first one is about a short introduction about laser welding systems for similar and dissimilar metals. I will only talk about metals, no plastics, only metals. And then the current challenges and opportunities to integrate digital technologies. And when I say digital technologies, to me it means machine learning, but also high fidelity physical model within laser beam welding systems. And then I will show a couple of case studies, basically two case studies, one around welding of battery packs and welding of e-drives for e-mobility. Why e-mobility? Because e-mobility is a very hot topic in UK. I guess it's also hot topic in India, probably is worldwide, and that's why I brought those two, let's say, applications for discussions today. So since we have 90 minutes, I have divided within three parts: Part A, B, and C. So Part A, we start with the technology introduction about laser welding systems. Then Part B is current applications of machine learning and physical model for predictive modeling. This will take another half an hour. And then we conclude with those two case studies. Now, I don't know how you're running the sessions. I'm very happy, and will be probably even better for me if we can have a very interactive session. So this means if you have any questions, any doubt, or you want to throw, any comment, feel free to do at any point in time. I don't think I'm able to see the chat, but again, feel free to shout and ask any questions at any time. This is probably the best approach.
So in that case, Pascal, okay, I can make it very simple. Okay, so during your lecture, if any student have any question, they can raise their hand and I can unmute him or her. Okay. He or she can ask question anytime, right? Is it
okay, perfect. Yeah, it's perfect. Thanks for this.
Okay. Go ahead.
All right. Okay. So now just quick introduction about myself, but even though I think you already have seen my, short bio. So just to say, my background is mechanical engineering. So bachelor, master, and also PhD. I did all my studies in Italy, University of Naples. Then nearly 12 years ago, I came to UK. And then since I came to UK, I started working on laser welding technologies. And since then, that is my main focus, is my main area. I am very much industrial driven, as you can see from number of automotive, aerospace, but also micromobility companies we have collaborative project with. We do also obviously we do fundamental research, but we try to cover to span between fundamental work and applied research as well. That's why you see all those companies here in this, let's say, in this table. For those of you, not probably familiar with the university and where we are or where I am affiliated with the WMG. So WMG historically, the full name was Warwick manufacturing group, in short WMG, and these days we only use WMG. Is a department within the University of Warwick. The university is within the Coventry, city. And if you see the map of the UK, Coventry is literally in the middle here. So this is the England. Yeah, let's say, yeah, this is pretty much, all this part is the England. In Coventry, as you can see, is pretty much within the geographical center of the UK. It's quite a strategic position, because within the Coventry area and within the West Midlands, we have most of the major automotive companies, including Jaguar, Land Rover, so JLR. We have BMW. Ford is not far away. We have Lotus, Aston Martin. So as you can see, is like so Coventry is like the UK automotive hub. So now our main focus is low carbon mobility, so net zero transportation systems. And everything we do, we try to align around low carbon mobility. So now looking at the joining technologies and laser welding, so laser beam welding. Laser beam welding is one of the core processes when it comes to let's say e-mobility and e-mobility manufacturing, and I will show you later. I mean, we'll spend probably 10-15 minutes around the current trend in e-mobility in terms of manufacturing, technology, impact, and sustainability. So you will see more, but just to say, laser beam welding has been growing quite a lot in the last few years, probably also because of the mobility. So in our lab, we cover different areas, as you can see. I call pillars. So pillar one is about the more fundamental material related kind of research, so laser to material interaction. The second pillar is about advanced modeling and digital twin. The third one is the process monitoring and control, ideally in process. We also do significant work and applied research around the full-scale prototype and production-ready validation. And then all those four pillars are supported by advanced testing and characterization. So testing, probably, I mean, you are very familiar with that. It means anything related to material processing, optical imaging, electron, so SEM imaging, mechanical testing, destructive testing. Okay, so anything around that, and we can do on let's say coupon level, but also on a sub component, so prototype level. So the lab, I mean, the labs we have available are quite, I mean, advanced on that respect. So yeah, so the spectrum of the research again is going from the fundamental work to all the way to the full-scale prototype. So I like those three images because they are, I mean, this actually is our lab. This one on the left has been taken, as you can imagine, with a nice exposure of the camera, so you can really see the, you know, the sputtering and, you know, the flash, the light reflected during the welding process. Again, so we do research on the fundamental, laser to material interaction, process parameters, impact of the heat input on the weld profile, if you are welding the similar materials on the face formations, IMCs, and so on and so on. But then we do again a lot of testing and validation on the full scale components up to pre-pilot studies for some of the industrial, let's say, partners. So just a short video. Probably I can jump on this, but just to say, probably, yeah, some of you have already seen WMG. So this actually is one of the welding lab. We are actually expanding these days. We are going to have approximate 100 square meter total within the next 4 weeks, where we can do manual welding, robotic based welding. Yeah, we can do inspection, control. We can retrofit, as you can see, I mean, we're pretty flexible with the setup. In this case, we were testing an active cooling system between laser welding of steel to aluminum. Yeah. Yeah, full-scale prototype, again, is fully automated system, which we develop completely ourselves. We work with a couple of vendors, suppliers, but all the design is done in-house. So we keep all the knowledge and all the know-how within our group. And I like to say advanced joining for sustainable mobility. So sustainability is something we are is a part of our core target goal. So whatever we do, we try to keep an open eye on the sustainability, and sustainability understood in terms of environments, but also economics and also society. Okay, that's why, I mean, even in this marketing video, yeah, I try to highlight the sustainability element. Now, so let's go to the technical bit, which probably is now, hopefully, is going to be more interesting. So when we say laser welding, is obviously a welding process. The difference between a laser welding and non-welding process is basically we use a laser as a heat source. Okay, so the heat source is the laser itself. And then depending on the way how the laser is interacting with the material, as you can imagine, since the laser is nothing else but light, different materials will have different reflection and different absorption. Okay, so eventually with the same heat input, so the same power of the laser, if you throw the laser on steel rather than aluminum rather than copper, you will have different behavior. So now those behavior we call welding modes. They are typically three. So this is how in the literature they are classified. So the conduction mode is only we are only melting the material, so there is only a phase change between solid to liquid. Then in the transition, we are starting approaching the vaporization temperature of the metal, and then in keyhole we are definitely above the vaporization temperature of the metal. So the benefit of the keyhole, as you can see, is a clear deep penetration. So you can really reach deep penetration. So the deepest weld you can achieve today in a single pass on mild steel material is around 70 millimeter. So what people have proved that they can achieve 70 millimeter, so 70 mil single pass on steel material using laser. Single pass, I'm highlighting a single pass because you can achieve 70 mil with multiple passes, but one of the benefits of using laser is also the processing speed. Yeah, so if you can do the same job in much shorter time, then you can justify, you have a reduction in energy, reduction in cost. So, you know, there is all the economical benefit going with that. Now, the keyhole, yeah, is something very attractive because you can reach very, deep penetration. However, the keyhole is also bringing a lot of challenges. Why is that? Because literally you have solid here, then you have the liquid layer, and then you have the, let's say, the gas region. So literally you have three phases. Actually four, if I count also the plasma. Yeah. So you have a solid, you have liquid, then you have gas, and then you have gas ionized, it's eventually plasma. So UV radiation. Okay. Why is challenging? Yeah, because we have all those phases together, and controlling and finding the equilibrium and the stability between those phases is nothing trivial. Most of the research in this area is exactly around on understanding the behavior of the keyhole, and then how to control the keyhole behavior to make it more stable. Now, when you see the physics, so this one probably the slide is a bit oversimplified, but when you see the physics involved, yeah, there are already, I mean, even in this table, there are 6 major physics. So the basic one is the heat transfer. Then obviously we have the fluid dynamics. Then there is impact of surface tension and also the bouncy force. Yeah. Why? Because there is a strong thermal gradient, vertical and lateral. So in basically in X and Y, yeah, in this view. So let's say X and Y. And because of that, as you can imagine, you can have a very turbulent behavior within the molten pool. And if you don't do it right, you can get a pretty nasty weld in the end. Yeah, this is one example. So this is something we have developed very recently. Actually is a full 3D simulation. Now we only see the cross section because we want to compare against the actual longitudinal section of the weld. So this one is welding of 1060 aluminum. You can probably, yeah, you can see also from the reference paper. This is a publication we got accepted basically last week. And you can see actually how the keyhole becomes unstable. So this is your solid. The red one is your liquid, yeah. And then the void here, this is your capillary, is your vapor capillary, and that is the keyhole. And you can see that if the keyhole is unstable because of the process, because of the power, because of the speed, because of the heat input overall, yeah, and then the keyhole is collapsing on the very bottom, and then once it's collapsed, is leaving behind pores, inclusions, and then this is matching somehow with the cross sections as well. So all those nasty inclusions, porosity, voids left behind, they are very often they're not acceptable by any quality standard. And then the research is about finding alternatives to the process. So eventually a different way of controlling the thermal gradient or the cooling rate in such a way you don't have those let's say defects in the weld in the end. So now when we talk about laser systems, there are typically three components. So the first one is the laser source. So the laser source is basically where you get the light generated. So as you can see, it's basically a cabinet you plug in to your electrical grid. So it's typically a 3 phases high voltage. And then you get in output your laser light through an optical fiber. So there are various technologies, as you can see. So historically, the most used, but this was already probably more than 20 years ago, was the CO2, so gas-based laser, with typically with the 10,000 nanometer wavelength. But then these days, CO2 lasers are still used. So there is still, good market for CO2 lasers, but the majority of the lasers these days are fiber based lasers. Either a disk, diode, or fiber itself. Okay, so this is basically what's happening in most of the cases today, and you can see there is a big difference in the wavelength. And as you can imagine, if I have a difference in the wavelength, so means different color of the light, then interaction with the material will be different, the absorption will be different, and all the thermal behavior will be affected, and as a consequence, the weld profile will be affected as well. So all anything related to the weld will be functional of the wavelength in the first place. It's quite interesting to see the wall plug efficiency. So some lasers are pretty good, some others are not so great, like only 50% efficiency. Why this is important again? When we are considering sustainability and energy consumption, this is something that very often is underestimated or is even ignored. But at the end of the day, energy consumption is one of the key elements that people are considering when we are counting the cost, the CO2 equivalent, the emissions, and so on. So it's always nice to have an open eye on the efficiency of the machine itself. Here it is. Is again some very, common chart. You can Google it. You can find from different sources. So this is showing on the horizontal axis the wavelength of the laser. Yeah, going from the UV, or let's say visible, and UV up to near infrared. And then we have different material. So eventually we have copper, you have aluminium. Okay, sorry, aluminium is here. Yeah, nickel, and so on. And you can see the behavior. So the absorbivity of different lasers with different color against the material. So the two materials which are extremely critical because they are broadly used in many applications within the battery pack manufacturing are aluminium and copper, and see how it is. So if we work with an infrared laser, so we are here, so this infrared around 1000 nanometer, the absorption for the copper is just below, probably around 5%. Yeah, very similar for aluminium. Probably aluminium is a bit higher, but yeah, we are in the range between 5 to 10%. So it means if you fire 100 watt power to the material, you only get 5 in the end. So it's a very, very low efficient process on the material itself. There are many challenges, which I will try to highlight, I mean, during this lecture today. One of the alternatives is to use a blue laser. So we are here around, the 450 nanometer. However, as you can see from this table, nothing is perfect. There is always a pro and cons between, different technologies. So the infrared is more portable, so you can tick most of the requirements. Yeah, you can fit with different vision systems, scanning head, monitoring devices, beam shaping, and so on. The blue laser, yeah, is very efficient to copper and aluminum, but has, let's say, some limitations when it comes to real, let's say, applications. One of the biggest limitation is the cost. So this is still too expensive technology, and wall efficiency is also quite low. Yeah, I want to also highlight this part. So laser by nature is something very dangerous. Yeah, you can kill people with the class 4 laser, high power. High power, I mean, we're talking even 100 kilowatts, 100 kilowatts, okay? It can be extremely powerful for welding. So when you see laser in industrial environments, those lasers are typically enclosed within a safety, room. It's fully enclosed. There is a robot, moving the laser around. However, these days, there is also quite significant development around handheld laser systems. You can see, I mean, a couple of commercial solutions, IPG and alpha lasers. The one from alpha laser is quite interesting. It's like you are wearing like a VR helmet. Yeah, see this guy? It's just like watching on a microscope with all the lenses, and then the laser is actually within this chamber. Okay, so this is quite interesting in terms of operation. So typical application. So this is the laser itself. Then the light goes through the fiber, it goes through the optics, and then is delivered here. So this is the delivery of the laser. Probably you can see the plume. So this application is typically for micro welding or for repair. Okay, so repair jobs. It's not very, I mean, widely used in industry yet, but I see a trend going up. So probably in the next few years we will see more of those lasers. Safety is an open point, and now I don't talk about safety today, but safety is another important element to consider. So just to let you know. Yeah, then also something we have to keep in mind is the way how you're delivering the light to the material. There are many different technologies, so I tried to summarize on the slide. Now, I don't want to go in detail on each component because it's too much, but just to say we can go from a fixed optics, so the light comes through the lenses, through the mirror, and goes straight to the material. Or you can have something a bit more sophisticated, like a wobbling optics. So it means there is a one or two moving mirrors. They can spin at quite high speed in the range of 1,000 hertz, so 1 or even 2 kilohertz. So by doing that, you can wobble the laser beam at high speed. And there are applications, especially for some materials like copper, where doing the wobbling is quite beneficial. Or you can combine a laser with a wire feeder. So you can bring a filler wire within the molten pool, and then you are locally changing the chemical composition of the molten pool. So this is typically used for aluminum welding, which is very crack sensitive, and you want to change the local chemical composition of the molten pool by adding an external wire. So this theoretically is very well known, I mean, in metallurgical engineering. So people are very well aware of the need of controlling the chemical, so the composition of the molten pool to avoid any cracking behavior. However, when it comes to system integration, as you can see, so the system becomes quite complex in the end. And then you can have the full freedom. So this is a full remote optics. We call the scanning optics. So the laser beam, again, is similar to the wobbling optics, but the working window can be even like alpha meter by alpha meter. So you can really move at very high speed the laser within a relatively large working window. So this one, scanning optics, is typically used for battery tab connectors, hairpin welding, in e-mobility. There are other applications outside, but today I want to only focus on e-mobility. Yeah, now this is interesting, probably more interesting from a research perspective, because we are approaching the elements, the discussion around digital twinning and machine learning and artificial intelligence. What is it? First of all, is the laser beam shaping. So the typical shape you get out of any standard laser is a single Gaussian. Yeah. So the energy profile looks like a Gaussian profile, and then if you look from the top, is like a circular spot. So just is a round spot. So this is more standard. However, these days there is a lot of research, investment, and development on something called the laser beam shaping. So shaping understood that we can change the shape of the laser beam in such a way we can control in a better way, the thermal gradients, the cooling rate, and the response of the material itself. Something which is which became quite popular is the possibility of having a donut, as you can see. It's like a donut ring profile. And then you can combine the donut with the core. Yeah, you can have basically two lasers in one, or you can have something very, anything. Yeah, like this one. This one is a tailed shape profile with the main round spot on the front. But you can have many other shapes. So these days, the most advanced when it comes to laser beam shaping is what we call dynamic beam shaping. So dynamic beam shaping in the range of, several megahertz, 50 megahertz. Yeah, this is up to 50 megahertz. Is a possibility of real time. Yeah, with 50 megahertz is exactly real time. So real time change of the shape during the welding. Okay. So you can go from a circular, eventually you can turn to a square spot, then you can go to, I don't know, pentagon or any free shape, okay? And this is one of the main research focus we have ongoing at this moment. So how to use laser beam shaping to improve the material response and how to improve the functional performance of the joint in terms of strength, and durability. Okay, so laser beam shaping is one of the core areas for us. Yeah, again, other examples you can see. Only spot, then spot with a bit of ring, and then only ring. Okay, so this is very flexible, and there are a few different technologies for enabling it, and we are trying to cover pretty much all the technologies we have in this table. So we have research programs pretty much with any of the technological solutions I have listed in this table. There are again always pro and cons, and that's why being research organization, we try to learn, all the plus, all the minus, yeah, in the technology. But why we do that when it comes to welding? Yeah, the main reason we want to have a bespoke weld profile. So typically you can go from something like this, as you can see, which is not ideal, to something more ideal. Yeah, you see, more round weld. How is this achieved? Yeah, this is achieved by again playing around with the shape of the spot. Or you can get a porosity reduction. So porosity, this is only now, the one I'm showing is a cast component. So the problem with that is hydrogen entrapment, which is driven again by the keyhole stability. So there is a way of improving the keyhole stability by, again, using the beam shaping. And the one most interesting these days, because there is not too much research ongoing, is the possibility of controlling the microstructure and eventually the phase formation, so IMC, again, using this logic of beam shaping. So this is one example. This is what we have done. This all those cases from our research. I just took, some good one, bad one to, highlight what can be achieved in the end. So what you see on the slide is an extremely active area of research. Okay, there are people focusing on these elements, other people are focusing on the stability, and then other people are focusing on the on the microstructure and phase formation elements. So it's extremely active. Yeah, so this one probably gives some visual understanding. So those are three cases of the same material. This is copper, welded with three shapes. So only core and ring, and only ring. Yeah, and then if you just watch now for a couple of seconds, and you observe the behavior of the molten pool, especially here, I mean, close to the keyhole, yeah, you can see how stable or unstable are those cases. Yeah, if you focus on this one on the right, yeah, you see the molten pool is very spattery. It's, you know, it's just ejecting stuff. There are spatters. Yeah, it's very, very unstable. Probably I can run again. Yeah. Then if you focus the one on the right, which is only the core, yeah, which is a very focused beam, very small, so very high energy density. Again, it's not too bad, probably better than the ring only, but still you see spatters flying around. So then the key is to find, I mean, this probably is expected, is to find the balance between the core and the ring. So the core is mostly helping in opening the molten pool. So you go deep, and then the ring is helping in enlarging the molten pool. And then by enlarging the molten pool, you are finding the balance between, you know, all the forces, all the load, all the flows involved within the molten pool, and then, you know, there is a better behavior in the end. So this is easy to say now, but there are a lot of challenges and a lot of opportunities for process modeling, predictive modeling, AI, which I will touch base in a few minutes now. Yeah, this is another case with the beam shaping. So there's also quite interesting research that one of our PhD students, yeah, Vivek, is doing. So this one was, again, high-speed camera. He used a DIC, so digital image correlation, to quantify the strain and stress involved during the solidification. Yeah, so this map is basically showing the transfer strain within the weld during solidification. And this gives quite useful information in terms of relationship between the stress, strain, the heat input, and the weld profile. So interesting enough, this is aluminium. So if you use this kind of beam profile, you have a very nasty central line crack. You see the red line? This is a central line crack. You can see there as well. Yeah, is aluminum welding. Then if you change profile, yeah, here you see there is a more core and probably less ring power. The central line crack completely disappears, although we are still having almost, as you can see, the same penetration. So it's very comparable in the penetration. There are some transversal cracks, yeah, here and there, which is still part of the investigation. But I mean, you can see the big improvement and you know, in the weld properties only by changing the beam profile. So the next area I want to touch is the monitoring and control, and this is extremely important when we are talking about you know, predictive modeling, because it's all about data. Yeah, it's all about collecting data, so it's all about sensors. So the typical question is as follows: okay, we have those welds, perfect. They are all equally rubbish. Yeah, let me say they are very, very bad, very, very low quality. How do we troubleshoot weld defects? Yeah, this is a question of 1 million pounds, I would say. Because once we have defects, the reason for the defects can be anything. Can be a gap, can be wrong process parameters, can be any mechanical variation, can be any surface contamination, can be any eventually change in the material itself, or even change in the thickness. Okay, so really can be anything. So within this area, probably the machine learning and the predictive modeling brings most of the opportunities, because this is exactly what machine learning is supposed to do for us, is helping in predicting and improving the quality of the system, in this case, laser welding system. And why within immobility, the needs of improving quality is even more important. Yeah, I just put some numbers. Now, obviously, I mean, there are different types, but if you take an average battery pack in automotive, so, you know, vehicles, cars, we have more than 10,000 battery cells. So each battery cell is welded to the terminal connector, and the terminal connector is welded to the bus bar. So if you put all together, and you multiply by number of battery packs produced by an average car manufacturer, you ended up millions of joint, so even billions of joint per year. Okay. So if you use a standard, Six Sigma approach, yeah, which is 99.7% confidence acceptance, out of billions, you ended up with several thousands of weld defects, which is not acceptable. So the target for machine learning is to be exactly at 100%. So the machine learning should be able to achieve 100% accuracy. If you're not at 100%, the machine learning doesn't help at all. Okay, so this is our target today. So we have a couple of projects working in this area, and we set a very ambitious target. We said, okay, we don't care whatever it is, machine learning, but we want to achieve 100% accuracy, which we understand is very, very ambitious, especially when we work with this kind of process, this kind of data, and data can be very, very scattered. Now we talk about data. When we talk about data, we have to talk about sensors. The situation is very diversified. You can have standard vision systems, so like camera or even like laser triangulation, or you can have indirect sensors like diodes. Diodes are very cheap, very simple to use. However, they are indirect. How they work? The diodes, by nature, by physics, convert electrical signal in light, or you can do other way around. You can convert any electromagnetic, spectrum, like UV light, visible light, or infrared light. So any light with electrical signal. So this is exactly how we use photodiodes for welding monitoring. So we just put a diode somewhere, yeah, let's say nearby, and then whatever radiation is emitted by the process is captured by the diode, the photodiode. And then this diode gives us, like in output, an electrical signal. And then by doing all the processing, the processing, signal processing with the machine learning, then we can get some correlation. Yeah, here it is. So it's a typical correlation of a diode, photodiode system. In this case, we have the plasma detection. Again, is a voltage. That's why you see the V here. But interesting enough, that in this case we did 3 weld condition, almost no connection, pretty good, well, acceptable weld, and then over penetrated joint. And you can see there is a clear correlation with the average signal of the sensor. Similar story if we are increasing the gap, yeah. If you are increasing the gap between the upper and the lower part, yeah, the signal is going other way around. The average signal is dropping, probably because the radiation doesn't only get reflected backwards, but also goes within the air gap here. Okay, so there is less reflection going back to the sensor. But end of the day, we see a correlation. There are other technologies, but I will go very quickly on this. It's called OCT, optical coherent tomography. With OCT, we are literally firing another laser, extremely low power, within the capillary, yeah, within the keyhole. Here it is, yeah, within the keyhole. So we are literally measuring the depth of the keyhole by firing one laser, low power, within the keyhole itself. Okay. So the principle is nothing new, probably for those of you doing, any material processing activity and characterization. So this is using the interferometer, so the microscope interferometer, which is a well-known technology. The key is how to use the same technology for monitoring the keyhole, knowing that the keyhole is never stable, it's always fluctuating. Yeah, there is always a vibration of the keyhole. And then how to align the measuring beam within the keyhole. So this is quite challenging, and that's why when you start collecting data, you see very scattered behavior. And we did some activity in this area as well to understand how to better, position the measuring device and get better, quality data in the end. This is more standard sensor, is a more standard, let's say, camera system, vision system. You can do process monitoring for linear weld, for circular weld as well. So this is more standard, and then you can retrofit some let's say laser triangulation, and then once we have those white line within the image, then using image processing, again with the support of machine learning, you can infer about the quality of the weld, or you can retrofit some useful information about the process itself. Yeah, this again is a camera system. This is for hairpin detection using LEV. So this is also interesting to show the impact of the background. So if you have a very shiny background, yeah, very low detection. And I haven't attended all the previous lectures, but the speaker was talking about data augmentation, and then all the tricks you can do with image processing to get a better classification. So this is one example of classification for laser welding. Yeah, here the score is 100%. So it means the classification algorithm, which is based in the background, is accurate enough. I mean, it can be more than 100%, and there is a good detection. So the detection in this case is really looking at those rectangular shape and this one. So those are the two parts you want to weld. Okay, so those are the two hairpin, 1 and 2. And you want to automatically detect. So once you do the detection, so eventually your center position, and then the laser goes on this point and then start firing and then melting the material and creating the joint. So detection here is very, very critical, because if you don't get the detection, you are eventually firing the laser in the wrong place. And if you're dealing with electrical components, electrical machine, there is a risk of fire or thermal runaway. There is always is a big problem. So there is a big research in this area as well. Thermal sensing, yeah, is another thing. Obviously, with the welding process is a welding, so we are dealing, the main element, the main physics is the thermal and the heat transfer. So possibility of monitoring the temperature is also significant and important. There are many, well, not many, but probably 2 or 3 options. One option we like is to use the thermal cameras, because they are non-contact. And they can cover a pretty wide field of view. However, there are limitations. One of the limitations is the extremely high sensitivity to the material emissivity, and emissivity is very much surface dependent, material dependent, and also temperature dependent itself. So I'm not aware of anybody who is able to measure very accurate temperature using thermal camera only by plugging the thermal camera and running it. You have to do some tricks, like some preparation on the surface, otherwise we'll never get a reliable measurement. Yeah, and then the next one, also quite interesting, is the possibility of using high-speed sensing, so high-speed camera, which you can retrofit within standard the welding equipment. So this one is quite interesting. This again is a collaborative research we have done with few colleagues over the last couple of years. Yeah, this one we did on purpose. This actually is a steel to aluminum. Yeah, it's challenging by material combination already. And we tried the different strategies, yeah, conduction mode and keyhole mode. And then we use also the high-speed camera to understand better the behavior during the solidification. Yeah, and I mean, by watching those videos and doing some processing on those videos, there is good learning coming out of it. And here comes the opportunity. We have data, yeah, so data is definitely available. However, from the data alone, we can't really monitor everything around the welding process. So what we are proposing is to have a more like a hybrid approach. So my proposition of smart systems or digital manufacturing is basically combining. Obviously, you need the process. Yeah, you have your process, the laser welding process is in my case. In your case, can be anything else. Many people are working in this area, right? So many people are trying to combine the process with some of the machine learning techniques. Like these days is very famous, the deep learning with the CNN. And anything around deep learning, or even this GPT, the transformers, which are quite high, providing high accuracy and high, performance. However, the main point about machine learning is data. Yeah. So if you have data and is a good quality data, then machine learning, yeah, definitely it works extremely well. However, if you have limited data, very scattered data, incomplete data, or the data is not even able to describe the full behavior of the process, then it's pretty much impossible you get the accuracy you are looking at. And that's why our approach is to combine a data-driven approach, so machine learning, with a physics-driven approach, okay? So within this loop. Now, creating this loop, yeah, is easy to do in PowerPoint, as you can imagine, but it's extremely challenging to do in, in real life because of, a few challenges to be solved. So the main challenge is probably on this level. Well, this is the requirement. We want to achieve a low computational latency. With the machine learning, once you complete the training, the latency is probably in the range of milliseconds, if not nanoseconds. But if you're dealing with the physical-based model, the computational latency can be in the region of a few hours, if not a few days, okay? Because we have to wait for the response of the physical model. So computational latency is one of the key, not the only one, but one of the key challenges when it comes to physics-driven machine learning. So these I also call physics-driven machine learning. So integration of machine learning with the physical model. So this is one of the driving challenges. Now, on this note, I want to just very quickly go through a bit of, let's say, history of the digital manufacturing. I'm sure everybody's familiar with, with the Industrial Revolution. So we started originally, with the steam engine. Then we jumped to, to the electric machine. And then we had, the assembly line, so mass production. That not very far away. In 1970s, approximately 1970s, we had the automation with the PLC. And then these days, but this again, as you can see, is more than more than 15, approximate 15 years old. We have the digital manufacturing with digital technologies. So why we do that? So this is one definition I have developed. Now, you might agree, you might disagree, you might like it, you might dislike it, probably. I mean, if you Google it and you put on Google definition of Industry 4.2 or definition of smart manufacturing, you will see millions of pages and with different definitions. They're all similar. They are all similar with each other, but everybody's trying to bring something. To me, the essence is data, computation, and the physical process all together. Why we do that? Because we want to be more flexible. We want to be more resilient and be able to adapt to the changes. Okay. And the final goal, as you can imagine, we want to produce with no defect, no waste, while we keep the cost down. We maximize productivity and capability. Okay. So this is the overall framework around digital technologies. And this one is what I like most, this definition. Just listen carefully. It's not mine. It's already, as you can see, quite old, but it can't be more appropriate than what's happening these days. The intelligent connection of perception to action. So basically, in a very sharp sentence, very short sentence, with 4 keywords, we have the essence of anything around the digital technologies, smart manufacturing, digital manufacturing, okay? So to me, this is really the essence. So intelligent understood AI, here it is. Plus the physical model, EM. Connection means we have the connectivity between the physical process and the digital element through appropriate sensing technology. Perception means we are able to sense in the real environment. And then once we sense, and then once we know what to do with those data, then we can take action. Okay, we can change the parameter, we can change the power, we can change the speed, we can change the frequency. Okay, so those are the actions. Again, very nice definition, which I use in my courses, in my lectures, very often, because it's very condensed, but it gives essence of the smart manufacturing systems. There are many ingredients. So again, I want to stress again that AI is one, then physical simulation is the second, then the automation element is the third, and then the connectivity is the fourth one. Okay. Our research in our lab is mostly focusing on the process itself. So the process is a welding process plus those two ingredients left and right. Okay. And we do some robotics as well. But in terms of research, it's basically contributing on the process itself. So we do innovation on the process. We do innovation on the process modeling, and then innovation in eventually new applications of AI for specific manufacturing challenges. Again, some statistics I want to show now, saying yes, there is a lot of talk, and even this workshop for you guys this week is about using AI technology for material processing or for manufacturing technologies. How much of those technologies, of those digital technologies, are really used today? So the statistics is not the most updated. It's 2020, I think, or 2021, probably 2021. So only a couple of years old. But adoption of Industry 4.0 per manufacturing sector. So automotive is leading the race, but only no more than, well, less than 40%. Yeah, so we are below 40%. All others are behind, including metals and mining. Yeah, metals is below 30%. It was below 30%. So automotive probably is investing more for a couple of reasons. Eventually, the main reason is because within automotive, we have extremely high production volumes. And there is a cost associated with the defect. Okay, so there is more interest in automotive to implement innovative digital solutions because there is a promise from those digital technologies to improve quality and reduce defect. You don't see aerospace in this chart for probably one reason. Within aerospace, they are very conservative, because there is high risk associated in introducing new technologies. So usually in aerospace, they think 3 times, maybe even 4 times before bringing any new disruptive innovation on board. That's why probably aerospace is maybe somewhere above in this list. Benefit, yes, I can jump on this, but now let me just highlight the challenges I see around this let's say digital technologies, at least when it comes to let's say welding, laser welding processes. So sensor is the first question. The first question we have to ask: do we have sensors available? Okay, perfect. How accurate they are? Are they accurate? Are they able to, capture what you want to capture within the given time latency? And when I say time latency, we are talking the solidification time. Solidification time is less than 5, 6, maybe 10 milliseconds. Maybe less, okay? So our control system must be quicker than that. Yeah, so must be like eventually 1 millisecond for data collection, couple of milliseconds for data processing, and then the rest for decision making and sending the signal back to the machine to make adjustment. And then data. Okay, we have enough data for training our deep learning model, machine learning model. Do we have enough? It's never enough. Okay, and then the simulation, the physical simulation. Again, is it accurate? Do we have computational latency? Yes, we have computational latency. How do we manage it? And then all the safety going, with those smart technologies. We can't ignore the safety and the ethics, with those technologies. Once things are online, everything is digital, then we have to think about, the safety. From a manufacturer perspective, is the eventually, protecting your IP. Yeah, you want to protect IP in such a way nobody can use your knowledge and your ideas. Again, this is an area by itself. Our work is probably around these 3 boxes. We don't do anything specifically on the safety side, but obviously, as you can imagine, there is other research covering that element as well. This probably now you are very familiar with the famous learning loop. Give me data, I will process it. Then once I've done the processing, I can identify the features, and those features will be the key landmark for training the model, and this goes in loop, as you can see. So this loop goes in many, I mean, a few iterations until I have, the right accuracy and the right, scalability of the model. Once I'm happy with this loop, then I can deploy the model, and then I can start integrating within the system. And even better, I can do the keep learning. So basically, the model has been pre-trained, is retrofitted within my machine. I have new data, and then the model keeps updating as we go. Okay. This is not always the case. So very often you have an open loop deployment. You do the training once, that's it, end of the story, and the system keeps working if you're really happy with that. In other cases, you keep updating the model as you go. So you keep retraining the model on the fly. So this is what we do for our training loop. Yeah. So in step 2 is our welding process. Yeah. Eventually you do the welding process with different process parameters, as you can see. Yeah. Bigger gap, small gap. Yeah. The power is changing here and there. Then you collect more and more data, and then your accuracy eventually is reaching, is going below the threshold. Yeah, and then we have the final deployment. Now, again, this is easy to say, but in practice there are many troubles, many issues, and many challenges. The driving challenge again is the decent level of accuracy, and accuracy always depends on the data, amount of data and quality of the data itself. Now, there are various techniques for improving the data availability. So one famous technique is data augmentation. So with data augmentation, you are basically starting from an existing, let's say data point here, and then you are somehow combining few neighbored points, so close by points with some sort of, let's say, interpolation or approximation, and then you are throwing another, let's say, data, augmented data. It's like, when you're taking images, photos with your camera, you're taking photos not only from one viewpoint, but from multiple viewpoints. If you don't have those viewpoints, then you can digitally create those viewpoints by data augmentation. Okay, so that is the main essence of data augmentation. Now let me show you one case. Yeah, so this one is a typical problem with probably most of the battery pack manufacturers are facing today. Sorry, I'm just noticed this is wrong because this paper is already published, so I have to update. But anyway, so the typical problem is, okay, I have my weld between, let's say, terminal to a battery casing. So the top one is the terminal, the bottom one is the battery casing. And I want to detect the amount of penetration, so amount of connection. If I have low connection, means my battery doesn't really perform electrically because there is a low connection. Probably there is no, current flowing through the connector. If there is too much penetration, as you can imagine, we have risk of burning the battery, and if you are burning the battery can catch a fire with thermal runaway. So there is a critical safety element, and everybody wants to avoid that. So we want to be in something like this. Okay, so the keyhole is open. So the keyhole was eventually up to here. There is a bit of melting there, but the laser doesn't go all the way through. Okay, the laser is reflected back, so it's like a blind keyhole process. So this is what we have done. So we said, okay, we did more than approximate 200 experiments with different combination of power, gap, and different processing conditions. And then we pulled all the data together. Yeah. So it just is a scatter plot of the data. In this case, I'm just plotting for the sake of visualization two features: the energy intensity of the signal and the scatter, so the noise level within the signal itself. And then question: Can we do automatic classification of the defects, knowing that we have three classes? Good one. Sorry, this is the good one. Lack of connection, and then over penetration, so over welding. Okay. Sound, lack of connection, over welding. So this is a typical classification exercise in machine learning. Yeah, supervised. This actually is a supervised machine learning. Where we have three classes. So we have 3 classes, and we want to classify the features according to those three classes. So if you are in a situation like this, it can't be simpler than that. Why? Because the classes are already far away with each other. Okay, so there is no overlap. However, when your classes are overlapping with each other, you have those gray area. So the gray areas are the enemy when it comes to classification. Why? Because if you have the gray area, it means there is either false positive or false negative. So it means misclassification, error, low accuracy. Okay. So what will happen in those cases? That eventually the same weld, assuming the same weld in reality is a good weld, might be classified as a bad weld. Okay. So then we have a false positive or false negative. Okay. So those regions are the regions causing problems. And then what we did in one research activity, again, this is already completed, just I haven't updated. So this activity, we said, okay, now let's see how machine learning works. There is no single machine learning techniques which can be used across multiple applications. So machine learning is always case by case specific. Okay. So the way how it works, we have to start training your model under, with your data. Once we have, the features identified, then you check the accuracy. Then probably you can do data augmentation if required. You can do cross validation to be confident on the accuracy. But you can't only use one single algorithm. So even for papers, if you want to write a paper, it's never a good idea to show a classification exercise only using one single algorithm. Why? Because as you can see from this table, different techniques are providing different level of accuracy. And the scatter is quite, it's quite significant. You go from something like, 89%, the worst one, and the best one is close to 97. 6-7% difference in accuracy. And in some applications, 6 to 7% accuracy, especially for the battery pack manufacturing I was mentioning earlier, is a big difference. The big shift into the prediction classification error. Okay. So even though we tested in this case like 6-7 different techniques, we couldn't achieve the target of 100%. So in this case, we had the 3 classes. We had approximately 200 data points with 2 process parameters. So 2 process parameters, 200 data points is quite reasonable. But even though that was not enough. Why was not enough? Mostly because of this gray area, which caused the misclassification problems. And this is where we have the opportunity of integrating the advanced, the high fidelity physical model. So it's basically this block now within this logical flowchart. So the question is why we can't do that. So the physical model, the CFD, FEM, techniques are quite advanced these days, as you can see from this animation. So this again is a recent paper we just completed very, very recently, probably a couple of weeks ago. This again is retrofitting the beam shaping within the picture, but now within the context of process monitoring and predictive modeling. This is pretty accurate prediction. It gives, in this case, good prediction of the porosity. Then with an elongated beam profile, you get also good prediction of the molten pool overall. So why we can't use those models? We can also, have a good prediction of the, let's say, of the material mixing. So if you compare the simulation against the DS, in this case, we have copper to steel. There is a decent prediction of the steel, so iron content within the molten pool. As you can see, there is a pretty good correlation. So simulation itself, so the physical modeling approach is quite accurate these days. Those techniques are much more accurate than probably 5, 6, 7 years ago, because more and more research has been developed within the physical domain. And there is also much more research. I see also, more publications coming where people are not only doing, physical testing and characterization, but they're also combining and supporting the findings through the physical modeling. So there is much more ongoing, and that's why accuracy is becoming pretty decent. However, yeah, I mean, there's another interesting things you can do. You can also see the velocity field. You can cross-link with your temperature distribution. You can see, I mean, from the simulation, you can see how the pressure distribution within, within the molten pool. You can see the bubble formation. So it's quite, I mean, providing quite useful set of information. However, the limitation is really how to use it to make it with low time latency, especially if you have millions of elements to be computed. Is a transient simulation, so you can have a very probably even below 200 millisecond time step. Maybe even few only millisecond in time step, and then computational time can be few hours, 15 hours. I mean even few days of computation. And then we want to test not only one single combination, you want to test multiple combinations, okay? Different material, different thickness, different welding profile, and so on and so on. So you can, this number can grow exponentially quite quickly. So if this is the case, we can't really use this technology, but we have to find an alternative. So one alternative which we have been considering recently is very new for us. So we are in the early stages, but we already achieved some result. So this technique is within the area of reduced order modeling. So reduced order modeling has been historically grown and being developed within the computational science domain. Yeah, so nothing to do with manufacturing or nothing to do with material science. So this is where reduced order modeling came from. The main reason, I mean, the main idea is to reduce the dimensional complexity of the model. So here I said we have 7 million eventually equations to be solved. So using the reduced order model, we are reducing the dimensionality, and then in practice, and means we are handling a much lower number of equations. That's why we call reduced. We're reducing number of equations, so we're reducing the dimensionality of the model. I like this one because it's just doing a like-for-like comparison between a standard machine learning and the reduced order model supported by machine learning. So the key element is here. So reduced order model is physics specific. So we keep the knowledge about the physics of the process, which we don't do within machine learning. So machine learning is a machine learnings are black box model. However, machine learning is non-intrusive. Reduced order model can be intrusive, okay? And that's why the beauty of this technology, of this reduced order modeling, is the possibility of working either only intrusive, so it means we are changing the constitutive equations, of the physics, like the Fourier equation for heat transfer, of the Navier-Stokes equation for the fluid flow. Okay, however, that is challenging because it requires very in-depth mathematical knowledge, of the partial differential equation. And that's why there is opportunity to use something more data-driven, which we call non-intrusive. Data-driven understood, we are still generating the data from a physical model. Okay, so data comes from the physical model. However, the processing is all non-intrusive using some of the machine learning. So this area here, reduced order model plus non-intrusive, is literally combination of machine learning plus physical modeling, PM. Okay, so this is probably the most promising one. So we have done some activities on this, and you can see here. So we compared the accuracy of the prediction of our reduced order model against the full model. So FOM stands for the full model. ROM stands for reduced order model. Using those two techniques. So POD Galerkin is an intrusive technique. So we are changing the constitutive equation of the FEM solver in the background. And then the POD RBF stands for radial basis function. So this is a pretty standard machine learning interpolation approach. And you can see, yeah, the error, how the error goes. So the intrusive, the accuracy goes extremely high. So the error is extremely low. When we increase number of, let's say, features, we call mode in the model. So it's below probably 1%. The non-intrusive, yeah, is okay, but we are limited by, in this case, no more than 10%. Yeah, so we couldn't achieve any more than 10%. So the reason for that was, so even though we increased number of features, yeah, the accuracy didn't increase. So what we realized that the accuracy of the non-intrusive technique is also about the, again, as you can imagine, the number of data points and the number of points that are used for training the machine learning techniques in the background. So there is a loop going on. So you can get very good accuracy with intrusive, but computational latency, yeah, let's put it here. Computational latency is a bit higher, better, yeah. Yeah, so it's like this. So 50 modes and for 50 modes. For the POD Galerkin is your intrusive technique. You see the time? We are saving 3 to 4 times. The machine learning base, so the non-intrusive one, 2.5 out of 3000. So there is 1,000 magnification. Okay, so we're really speeding up in this case. But accuracy, as you can see, yeah, we are comparing 2% against, well, more than 10%. Yeah. So there's always a balance between accuracy and cost. But I mean, from research and development, so that there are opportunities of using some of those technologies, some of those, let's say, techniques, if you are facing a specific challenge in managing the computational latency by having a decent accuracy. So just to let you know, probably you know this already, in most of the slide, I have left one of the paper or one of the research activity we have developed. So you can always Google the paper, you can download, you can read if you find anything interesting. And if you have anything to ask, I mean, you can always drop me an email or be in contact. Now, the final bit, I think we're approaching the end now. Before jumping on the couple of applications, so I think I've been talking for more than 1 hour now. So any questions?
Participants, if any query, please click on the raise option. So we will unmute your. Participants, if any query, please raise your hand so that Professor will reply.
Okay, if not, I can carry on a bit and then I can leave a few minutes in the end for final question. Yeah, okay.
Yes, sir, you can proceed.
Yeah, okay. So now the next and the final bit is about, I mean, a couple of applications. I want to start with this one. This again is a public available data that everybody and every politician is saying is promising, okay, the electrification, with electrification, we are saving our planet. It's true, but only in theory, not in practice, as you can see. Why is that? Because if you compare, you know, the electric vehicle against the internal combustion engine, yeah, in service and in use, yeah, there is theoretically no emission, but we have to produce those vehicles and then we have to dispose those vehicles, you know, end of life recycling. Not to mention the raw material. So, you know, with all the mining, eventually using also some of the rare metals as well. So there is a big impact of the EV manufacturing in terms of, you know, environmental impact of EV manufacturing. So that's why we have to really keep, we have to observe this space, yeah, because otherwise we can make another disaster. So laser, yeah, this again are public statistics. This is what I mean, what we see in publications and press release and you know, article magazine. is that yeah, the laser material processing cover between 60 to 80% of all the material processing applications for EV manufacturing. Okay, so it means the laser is playing a big role for EV manufacturing, and that's why when it comes to research and development, we can play a role within this this space. So now I will show you a couple of applications. The first one is very aluminum intense. This is typically recycled aluminum from post-consumer scrap. It's a 6000 grade aluminum, which is very well known to be crack sensitive. So this material, when you start welding, given the nature of the material and you know, the freezing range of the material with the silicon, yeah, it's very sensitive to cracking. And obviously, if there are cracks within the weld, yeah, you don't achieve any performance or any structural performance at all. So you want to really get rid of the cracks. This is not only challenge, yeah. So the challenge for manufacturing those battery casing is also about the dimensional integrity. So we have to manage the heat input from the laser in such a way there is neglectable thermal distortion in the end. So we tested various technologies. One of the technologies we have tested is the possibility of modulating the power and oscillating the laser beam. So now if you see the cross sections, yeah, this is quite, I mean, interesting result. That if you weld straight away without, you know, paying attention to anything in detail, yeah, you still get a connection. From outside, looks not too bad. So I mean, it's still there is a connection, but then when you analyze the weld, the profile is very nasty. So this going from left to right took some time. As you can see, it's not only changing the parameter, was changing the overall welding strategy, but then you can achieve a pretty good weld in the end. So this one, the result you see on the screen is really combination of testing, you know, the physical part, optimizing the parameters, selecting the welding geometry, running, you know, the physical simulation in the background, and then using some of the data processing and classification to eventually find correlation between input and output. So now the result on the screen is good, but I mean, in order to get to this point, there are significant steps. Yeah, this probably I can jump. Yeah, I can show you this one. So this one shows two different welding strategies. Yeah, no oscillation and with oscillation. So the reason of using oscillation, yeah, the conceptual reason is basically here on the left-hand side. We want to use the oscillation in such a way we can maximize the speed of the laser. By doing that, we are keeping the heat input lower. But at the same time, we are still melting enough metal for, you know, creating the joint. Okay. And now again, from a process modeling perspective, understanding the frequency of the oscillation, understanding the amplitude of the oscillation is something not obvious at all. And again, this is something we've been developing also by running in conjunction, you know, our predictive modeling. Yeah, so then I will show you this one, which is probably less, let's say, academic relevant, but since we do quite a lot of research in this area, a lot of applied industrial research, I want to show also the overall capability, I mean, what we can achieve in the end. So it's not only proving the concept, improving the technology, it's also deploying the full process ready for the, you know, for the end users. And this one was a perfect example of taking the research and all those digital technologies, sensing, you know, machine learning, predictive modeling, retrofitted completely within the hardware, within the machine, and then, you know, ready to be taken by the end users. Yeah, so the next one is a copper hairpin welding. So this now we are firing the laser on top of those, you can see here, those hairpins, those are copper hairpin. So copper, I already said, is extremely reflective to laser, especially infrared laser. And also, when we have those hairpins, yeah, you see those two images, we have to manage the tolerances. This is ideal. Yeah, it's perfect. You see, flash, no variation. But in reality, you might have some misalignment, some offset, and so on. So how do we manage those variations using the laser? So this one was a perfect exercise using the beam shaping. And when it comes to beam shaping, is a perfect exercise for combining digital technologies, predictive modeling, and image processing to find the optimal profile of the laser beam. So if I played again, is a high-speed video. So let me play with this one. No, let me start with this one first. Yeah. So just see here. So those are the two hairpin, the one on the bottom and the one on the top here. Yeah. The laser is going all the way around. Yeah. And since there is a gap in between, the droplet is forming, but is dropping within the air gap. Only after some points, yeah, see, you're melting more, then only after some points, yeah, you start getting a build-up of material. But again, see, it looks very sputtery. So if you do the other, means the same with the same material, with the same gap, but using a different beam profile, which again was optimized through simulation, then yeah, same philosophy. So the laser is going around, but you see much less sputter, so it looks much more stable. Yeah, it's melting, and the liquid starts building up. You can imagine you keep the molten pool open for probably 100 to 200 milliseconds, and then by doing that, yeah, you see, you start bridging, the gap. Here it is, and this looks much more stable than the other one. So just to say how many things you can do in this in the space of combining the knowledge, the process knowledge with the characterization plus digital technology. So this is kind of fascinating area which keeps growing as we are talking. Yeah, and then I mean, just to quickly close on this, then I mean, this is also proved by the strength of the joint in the end. You see, so 0 BSS means we are here, only the core, and then BSS 0.6, yeah, 0.6, we are with this different beam profile. Yeah, the strength is 3-4 times higher. So there is a clear, why is that? Because there is less porosity. Yeah, probably the image is too small, but if you zoom in a bit, you will see there are big pores in there, and this is the case for this weld. So clearly, this approach helps in improving the the stability and reducing the porosity in the weld. Okay. So I think it's everything. We have probably 5, maybe 3-4 minutes, maybe a couple of minutes for questions. So thanks again, and let's start throwing some questions if you have any questions.
Thank you, sir. Such a wonderful talk and an in detailed explanation. So participants, session is open for discussion. If any queries, please raise your hand. We will unmute your mic.
Okay, so I guess there is no question then.
Yes, sir. I think no one have questions.
Mm-hmm.
Once again, thank you from our side, sir.
Yeah, thank you. Thank you again.
Yeah, Pasquale, it's Soumitra.
Oh, yes. Hello. Hi.
Hi, Pasquale, it's a nice man. You are genius. Means you saw a lot of things. Means we can do a lot of things. Means we can use AI in different, say, laser processing, laser welding, laser cutting, and e-mobile, right? So yeah, it's a very good discussion. Okay, thank you for accepting my invitation for this talk, and catch you soon.
Yeah, we'll be in touch. Thank you.
Yeah, thank you. Thank you very much.
Thanks. Take care. Bye-bye.